Thank you. All right, so I will be talking about the Gibbs state of the mean field Bose gas, and the first question I should answer: why do I talk about that here, right? So the point is, we have seen quite some talks about approximations of quantum systems. Maybe not many-body, but at least few-body. And this is about it's about an approximation result for a Gibbs state in terms of a simpler state. And so you should really take this as a motivation. I mean, this is an example where we can prove something where an approximation holds, okay? And that approximation is somehow in terms of quasi-free states, which are Gaussian states, although the resulting state is not quasi-free, it's not Gaussian, okay? But it will be, well, it's given in terms of Gaussian states, okay? So that means here we have an example where we can prove something in a large particle number limit, okay? And although this model is, I mean, to some extent a bit artificial, it's a mean field system, still it has very interesting mathematical structure. And given this result, you can expect that this can be extended to more realistic systems. Okay, but let's get started. And well, I mean, I mainly want to make you understand, okay? I don't need to come to a theorem or something. So if you have any question, please ask, okay? Okay, let's get started. This is a gas. So we're talking about a gas of particles, and it's wiggly lines because it's quantum mechanical particles, okay? So that's what we're going to talk about. And I mean, most of you know, but just to be just to be sure that we're starting on the same page. So I'm talking about Bose Einstein condensate. So what is a Bose Einstein condensate? Maybe first of all, let me read that quote because it's so nice. It's by Wolfgang Kehler, who won the Nobel Prize in Physics in 2001. And he says, Bose-Einstein condensation is one of the most intriguing phenomena predicted by quantum statistical mechanics. So that should be motivation enough. And what is it? So, well, it's the effect where, I mean, you have a large gas of particles and you cool it down sufficiently much. And what you observe is that below a certain critical temperature, which is indicated here by Tc, a macroscopic fraction of all particles starts to do exactly the same thing. And it's really exactly the same thing, and you can observe that in experiments. Okay, so a part of the system acts or behaves as a giant coherent matter wave. Okay, and here we have a picture. So from the left to the right, the temperature the temperature decreases, and that blue peak that you see emerge in the middle, that's the Bose-Einstein condensate. That's a macroscopic fraction of all particles that condense into a mode close to zero momentum or velocity. Okay. Now, this happens in gases of bosons, which are, well, quantum mechanical particles with symmetrized wave function. We will see that in a second in the mathematical setup. And well, because of this, such systems display a wealth of interesting phenomena that are all related to either the BEC phase transition or to the presence of the Bose-Einstein condensate, okay? And this is very difficult to study mathematically, usually, because, well, as you all know, we have a curse of dimensionality in the system. And also, I mean, often in physics, you use perturbation theory to understand such systems, which is, however, from a mathematical point of view, a terrible tool because of small denominator problems. So this is mainly to say that, I mean, not that perturbation theory is bad to understand these systems heuristically. It's rather to say that, well, if you want to understand that mathematically, you usually need to come up with other techniques, okay? All right. And of course, that says nothing about numerics. All right, so let me see. So here is our gas of particles again. That's for me above the critical point. This is below the critical point where a giant matter wave has formed. And also the other particles, the wavelength seems to be longer now, and that's the system at 0 temperature, okay? Almost all particles do exactly the same thing. And I will be mostly interested in that picture here, where we have a Bose Einstein condensate, but also particles outside. And typically this will be order n particles outside, order n particles inside. Okay. And now let's come to the mathematics. So what is the mathematical formalism? Well, we have seen that before too, so I go over it rather quickly. We have a Fock space, the bosonic Fock space. We have symmetric wave functions, so permutation symmetric. Whenever you exchange the coordinates of two particles, it's the same function. This is this line here. And here is the Hamiltonian of the system. This is probably more important. So we have the sum of Laplacians. These are the kinetic terms, and we have an interaction. And so you should think of the following situation. We have a box, or let's say a torus, of side length 1. And that function lives on that length scale. Okay? In that sense, it's a mean field system. Everybody can, in principle, interact with everybody. Or say, you interact with order n particles. And to make those two guys balanced, we put a 1 over particle number here. Okay?
Is it attractive, repulsive? What's the shape of V?
It will be repulsive. So I think of a repulsive gas. Okay? All right. And, well, here you see it's a grand canonical model. So it's a Hamiltonian on Fock space. 1 over n will be the expected number of particles in the system. Okay?
Is it a bound system? What keeps them together?
Well, it's on a torus.
It's confined.
It's confined. It's on a box, side length 1, periodic boundary conditions. Okay.
Could it be to enforce this by having a V that has...
Sure, of course, absolutely. I mean, I do it here first. I mean, as you will see, I mean, that result that I'm going to present is not easy to get. The paper's like 100 pages. And while you can certainly do it also for a trapped system, but then, for example, the condensate wave function is not as simple. You need additional analysis, and we wanted to get rid of that. But in principle, you can think of that. I mean, this certainly works also for a trapped system. Okay? All right. Now, we have seen this also before, but again, to be sure, we have the creation and annihilation operators on Fock space. The creation operator creates a particle, and the annihilation operator annihilates one. We have the commutation relations, and using these operators, I can write the Hamiltonian in second quantization. And this is how it looks like. So we have the kinetic term. I mean, it's in Fourier space. The minus Laplacian, the spectrum is p squared, with p in 2 pi z3. And here, this is the Fourier transform of the interaction potential. Okay, if you have questions concerning that, please ask. So it's just, I mean, it's not, I mean, if you have not seen it before, it's not easy to see, but it's, just believe me that this is how it looks, and these are momentum sums. Yes?
The interaction, is it a contact interaction? Is it a contact interaction that you're considering?
No, it's not contact. So it has a, I mean, just think of a Gaussian, positive Gaussian.
So the VP is also a Gaussian?
VP is a Gaussian, yes. Okay. And as you will see later from the result, we need that the Fourier transform is non-negative. Okay? If not, that doesn't make much sense. Okay. All right. So if you're okay with this here, you are. Then let's go on. What are the quantities I will be interested in? Well, it's mostly the Gibbs state. Okay, but well, the Gibbs state always goes together with an energy. And well, here, so for physicists, this is maybe a bit strange to denote this as free energy. I mean, I will be interested in the grand canonical ensemble. Okay, and usually the usual thermodynamic potential is the grand potential or the pressure, right? This here is, I mean, this here is the grand potential. I add mu n to have an equivalent of a free energy. Why do I do that? Well, the point is the formalism I'm using, or the results, I mean, how I state results is the following. I will choose the chemical potential such that the expected number of particles in the system is always n. We could do it differently too, but it's just a way, you know, I had a 1 over n in the Hamiltonian, and if that's not the expected number of particles, the formula doesn't make much sense, okay? So this is just to make it easier digestible, okay? Let's put it that way. So that is, we have a grand canonical version of the free energy, and we have the usual grand canonical Gibbs state, and the chemical potential is always chosen such that the particle number is n, and I will be interested in a large particle number limit, okay? And, well, if you start to scale one quantity, you also need to scale other quantities, okay? And so what is the right temperature scale? Well, the right temperature scale is the temperature scale on which the BEC phase, the Bose Einstein condensation phase transition happens, okay? That means what we will be doing is we choose, this is the inverse temperature as kappa times the critical temperature of that phase transition, okay? And we know what that is. I'll motivate it in a second. And so the beta C is this here. It scales with n to the minus 2/3. Okay, that is strange, right? Why does a temperature scale with n? Well, I said if we scale one quantity, maybe we have to scale another. But the true reason is I said we go on a box of side length 1. And usually the inverse critical temperature is proportional to the density to the power minus 2/3 in the ideal Bose gas. And there is a free parameter in the system. We have one free parameter in the system, and we just choose the length scale to be 1, okay? So trust me, this is the right temperature scale, and there's nothing scary about this being independent. We could also make the box large, and then that wouldn't be independent. But then you have another free parameter, or in one choice. We just make that choice, okay? And this is explained on the next slide. So if you take the ideal Bose gas, right, and you look at, so this is the Gibbs state of the ideal gas, no interaction. This is an exactly solvable model. Okay, you find it in any physics textbook on statistical mechanics. And you make your computation, the expected number of particles in the system scales like that here. The expected number of particles in the condensate scales like that here. That means in the zero momentum mode. This here, the A0 star A0, this is the creation and annihilation operator of the constant function, okay? So if you look at the expected number of particles in the zero momentum mode, it scales like that here. And that means if you choose beta on the scale of beta C, say beta is equal to kappa beta C, so that means for kappa larger than 1, this scales proportional to n. If kappa is smaller than 1, this here is 0, okay? So the leading order behavior is 0. And this is, we have a BEC phase transition in the system, okay? And, well, the critical temperature is that here. And again, you could also, actually it would be rho here, but we set the length scale equal to 1. Good. And, well, so the important message is this behavior persists in the interacting model. Okay, so let me quickly say a few words about the literature before I speak about our results. First of all, does that make sense? I really want you to understand that because it's important. Are there any questions?
So where does the dependence of beta C from n come from? Like the first line I understand, you just say I made the computation, I get exactly that number, n times that. In the second line, the beta C, also they come out of the computation. So you just make the computation, you find n times, and then you get that.
Okay, let us do it the following way. Let's take really a limit where we let L, the length of the torus, go to infinity, and let's do it in such a way that the density is fixed. Okay, if we do this in our head, the only thing on that slide what changes is that you get a row here. So you let particle number go to infinity, length go to infinity, the size of your torus, such that n over L cubed is constant. It's rho. Then you find this formula. The beta is of order 1. The beta c is of order 1. And then you see, from this formula, this is what you get. If beta is larger than beta c, well, then, maybe you divide by n because we have taken a limit. Then you see, well, this here is non-zero. But if beta is smaller than beta c, well, you get 0. And that is exactly your phase transition. So that means from this limit, you see that if beta c, if you choose it the right way, you find that phase transition. This is how it happens. Okay. Okay. Good. Then let's see, what do we know about that model? Okay. First of all, we know something about the excitation spectrum. That's the first two, actually the first three references, okay? We know something about the excitation spectrum, and well, I will explain that more on the next slide, but for those of you who know, it's given by Bogoliubov theory. So the typical computation done by Bogoliubov in 1947, what you do, and let's have a look here, is, well, if you are at 0 temperature, you expect that almost all particles are in the Bose Einstein condensate. Okay, this is what you expect. And these operators we have seen already, when they act on something, well, if this guy, for example, acts on a state with n particles in that mode, in that specific mode, then you get a factor square root of n. Okay, this is how these guys are defined. It's true for both. Square root n plus 1. That's not important. So that lets you conclude, if you have a lot of particles in the 0 momentum mode and much less particles in the other modes, well, then the 0 momentum mode should be dominant. Okay, and then you make an expansion. What you do is, well, first all of them could be 0. That gives you a number. But then you have, well, by symmetry, 2 of them could be 0 or none of them. 3 is not important. And so what people do is a C-number substitution. So you just replace, and this is a bit strange, but you can justify it, you replace the operators with 0 momentum just by numbers. And if you do that, you get an exactly solvable model. Okay? And, well, it is a model which is quadratic in creation and annihilation operators. You can diagonalize it explicitly by a Bogoliubov transformation, and you get an explicit spectrum. We will see it later. Okay, so this is the content of the first 3 references to make that rigorous for that model. So this is really about the low-lying excitation spectrum. It's about the ground state, and it's about the low-lying excitation spectrum. Now, well, let's introduce the temperature. I told you we know that there's a BEC phase transition. Well, this has been showed in these 3 references for slightly more complicated, for more complicated models. But it clearly applies to the one that we have here. Okay. Now, in these references, so that means we know that there's a BEC phase transition. In these models, what people have studied in these papers is what happens at the critical point. So you expect that at the critical point, you can approximate your system by a field theory, okay? And that has been discussed in these references. So for this model, you can do that. Okay. Now, what I'm interested in is not really this specific parameter regime or that one here. I'm rather interested in getting the whole picture. So seeing the condensed phase, seeing the non-condensed phase, seeing the phase transition, and finding an approximation of the Gibbs state in these parameter regimes, okay? This is what I'm interested in. And this is the result that we have. Okay, so what we can show is that the Gibbs state, and I will stay on that slide for a while, so we have time to understand this peacefully. Okay, so the Gibbs state can be approximated in trace norm by this state here. Okay, and let me explain that carefully. What is what? So first, we have here a part describing the condensate, and here a part describing the thermally excited particles. Okay, how is the condensate described? Well, it's described by a coherent state. Okay, I don't know, have we seen this before or not? Probably not. So a coherent state is well suited to describe a Bose Einstein condensate. It's basically, I mean, you would say a Bose Einstein condensate could be like n0 particles in the p = 0 mode. That would be a Bose Einstein condensate. However, that doesn't come out in the grand canonical setting where the particle number can fluctuate. Okay, this state is peaked around a certain expectation value. It has the variance is on the same order, so it's really a peak thing, and it has a certain particle number variation, but it's not so bad to think of that guy as roughly describing n0 particles, which are in the condensate, okay, in the constant function. So this fancy exponential is only giving some fluctuation to it. Okay, then what's next? Well, here we have another Gibbs state, and this describes the thermally excited particles. And how does it look like? Well, here's a kinetic term, and that's exactly the same guy as here. Okay, it's exactly the same guy as here. And then we have an interaction term here. And the interaction term is quadratic in creation and annihilation operators. So where does that come from? Well, I told you here that, so let me write down this formula because it's so important. So A0 acting on a state with n0 particles, and now let me not screw this up. This is square root n0 minus 1. So that means the number of particles that you have in a certain state determines how large this operator is going to be. Okay, and the largest you can have is square root of the particle number. Okay, and here we are in a situation you can have, let's say, half of the particles are in the condensate, half of the particles are outside. Okay, but we have only one condensate. One mode has order n particles, and that's the zero momentum mode. All other modes will have much less particles. Okay, because of that, all the operators here where the momentum is 0 will have the largest contribution. Okay, and at 0 temperature, you have almost no particles apart from that. But here you do. Okay, but nevertheless, the action of these operators will be less relevant in some sense. So what you do is a C number substitution. Okay, this is basically you are replacing A0 and A0 star by square root of n0. This is your expected number of particles in the condensate. Okay, so if you do this, and you get this n0 here. So you have, first of all, you have terms where you have 4 of these with 0 momentum, but this goes somewhere else. This is only the condensate, so this should be somewhere here. Then you have those where you have only 2 guys, that's here, and the other guys are not relevant by symmetry, okay? But you need to justify that. Okay, so this guy here is used at 0 temperature, but now it's a bit different. It's at 0 temperature, you have n here and not n0. So this guy is really temperature dependent. And you have phases here, which come from that. So that means these two guys actually coupled, and that's important. Yes?
In this replacement,
Yes.
when or for which interaction is that actually a good approximation? So I'm thinking of liquid helium, for example, where the condensate fraction is
understand.
smaller.
Yeah.
So it depends somehow. It should depend somehow on the interaction.
Yeah. So the question is basically, is this only a good approximation if you have a lot of guys in the condensate? And the answer is no. It's always a good approximation, because either this is a very important mode and you capture it correctly like this, or you have few particles in that mode, and then you can do the approximation. It won't help you, but it also won't hurt you. That is basically the logic. And it's mathematically, there's a, well, this is very well understood. All right. So that means we have here a Bogoliubov Hamiltonian that is coupled via these phases to that guy. But this is an exactly solvable model, okay? So if we want to compute expectations in that guy, we can do it. It's just a matter of sitting down and applying algebraic rules. For example, the Gibbs state here of that guy satisfies a Wick rule, okay? So you can compute. However, here's one important point. You have these two terms, and then you integrate against something. So you take a convex combination. So the G is a probability distribution, and this G contains terms, well, where 4 of these guys are 0, okay? And this you see here. So we have, so we could replace it by squared and 0, but actually we have the Z, okay? So each of the A's that are made to 0 come with a Z here. So this is Z to the 4. This is the term here when all A's have a 0 momentum here, okay? So V hat of 0, this is an interaction term here. Also, this comes from the chemical potential, okay? This is to get the right particle number. And well, this is a probability measure. It's like a one-mode phi to the 4 theory. And you integrate this state against that. And here's an important point. That makes your state non-quasi free, okay? So if you look at this, this here doesn't have a definite particle number. This here also. So these two guys don't commute with the Hamiltonian, but your original Gibbs state does. So you shouldn't approximate, or you cannot approximate something that commutes, I mean, that is block diagonal in the number sectors of the Fock space with something that is not. That doesn't work, okay? So how is that restored? Well, by this integration. So you integrate over all phases, and by that you restore the number symmetry, okay? So by this integration, you get a state which is non-quasi-free, and it commutes with a number operator. So it's block diagonal in Fock space, okay? And, well, this is what this guy does, okay? So it's sort of a quasi-free approximation, but not really, okay? And this term also implements the right particle number fluctuations in the Bose Einstein condensate, okay? So, okay, that slide was not so easy. Are there questions concerning this?
How do you find it?
Pardon?
How do you find gamma?
How do you find gamma? How do you prove this?
Or even guess something in this direction?
That's a good question. It took us a while. Oh, basically 4 years. No, I mean, how do you get there?
I mean, no, and you cannot start from.
No, it's a perfect question, and I should have answered it right away. Let me answer it now. So what is the heuristics behind this for me? So first of all, I look at that guy, and well, the eigenfunctions of the Gibbs state and the eigenfunctions of that guy are the same, okay? Because the Gibbs state is just a function of that guy. Now I think about the following. How could a typical eigenfunction of the Gibbs state look like? Well, it certainly has a certain number of particles in the condensate depending on temperature. This is this number here. If I assume that's the case, then I look at that guy here, I make the C number substitution in my head, and I start collecting terms. First, terms that only concern the condensate, I find these here. Then I collect the quadratic terms, they go here. Now, by symmetry, there can be no guy with 3 zero momenta here. Okay, let's forget about that. But then are quite some more terms. So one guy having 0 here. Then there is none of these having 0 here. And well, they are there, and they are not small. So the key point that you need to understand is you need to group these terms in 2 classes. The first class is they don't change the structure of the Gibbs state but are large. For example, there are interaction terms which are of the form, which lead a contribution of the form v hat of 0 n over 2. This is just a number. This we like, okay? So we find terms of that form. They are large, but they don't change the structure of the Gibbs state. They are not operators. They can be approximated by numbers. And then we have to then we have to prove that the remaining terms, so a Gibbs state is e to the minus beta h. We have to prove that beta times the remaining terms are small, that we can neglect them. And if you go through this, you can get a guess for this. But to be honest, this formula we only see after 2 years of work. Okay, so it's not easy to guess. Yes?
Maybe just to get an understanding together with this question. Of course, in the super stupid case where I don't have interaction, then at least the structure is there, right? So
well, if you have no interaction, then this exactly. Guy is gone.
Exactly,
and
but
that
I think, at least for me,
yeah.
even to arrive at the first line was not the first line of your slide, right? The structure, you brought the gamma. So maybe for a person which is like me, is not really used to that, the fact that the gamma might be looking like this with some effective Gibbs state, and then you need to talk about what it is. Then,
sure.
Yeah, that
sure.
The form like this, so maybe you expect that it might look like that. And then the question is, what is the Hamiltonian that I need to
What is the Hamiltonian?
And from there you can maybe write, I guess.
And maybe let me mention one thing. So in the non-interacting case, the fluctuations in the particle number in the condensate is much larger than here. So it gets damped down by the interaction. And it's not so clear by what, okay? Yes?
The small g.
Say it again?
Small g at the bottom.
Yeah.
So where does it come from? Because it has a bit of a flavor like a Mexican hat thingy.
Yeah.
So
yeah.
How much of the physics is in there, is put in there? How much is coming from there?
Okay, so this describes the Bose Einstein condensate, and it's basically what you get if you take the interaction terms coming from here and you put them together with entropy and you minimize that. This is where it comes from. It's a Gibbs distribution. It's basically coming, so you can do a kind of semi-classical approximation, and this leads to that. You take the interaction terms from there and you bring it together with entropy.
Then you integrate out all of the other modes except for the zero mode.
Yes.
Okay.
Yes. You can prove that you can separate these modes from the others to some extent. I mean, the Z's talk to each other. Okay.
Can the sign of mu change?
The sign of mu can change. Yes. So the sign of mu will be positive in the condensed phase and negative in the non-condensed phase. This is how you can see the phase transition, actually. Okay. Any more questions concerning this? Okay. So now, with this at hand, you can actually prove a lot of interesting approximation results. So you can use this to compute a lot of quantities, okay? And here's one example. It's the two-particle density matrix, okay? I won't go into much detail here, but the main point here is this could not be computed before. So we didn't know how to compute that at positive temperature, and we need new correlation inequalities to do that. I will speak about that in a second. So which is one of the main technical contributions here. Okay, so we can compute the one and the two particle density matrix. One particle density matrix is not so hard. Two particle density matrix is very hard. Okay, and from this you can see that the correlations are a little bit looking like quasi-free, but they are actually not. So that's an interesting part. Okay. So what is maybe easier digestible is you can look at the number of particles in the condensate, okay? So that's a random variable, okay? So you can ask the question, how many particles do I have in the Bose Einstein condensate at different temperatures? Usually one computes the expectation, okay? Here we can do much more. So let me define the random variable n0 by saying the probability that n0 is an AB is this trace here. This is the standard definition, okay? This is just a spectral projection, okay? So I can define this probability, I can define this random variable, and this is really describing the number of particles in the condensate. It will not have a definite value, and it will have fluctuations, and well, the question is, can we say something about that? And indeed we can. So first of all, this is the first slide. This is simple. This is not hard to get. We can show that the expected number of particles in the condensate scales to leading order, or is to leading order given by the ones in the ideal gas. So the interaction doesn't change that to leading order. Okay. What we see, however, is that the variance is changed by the interaction. Okay. The variance of the number of particles in the condensate in the non-interacting system is order n squared, while here it is n over beta. Beta was scaled as n to the minus 2/3, so this is n 5/3. So that means the interaction damps down the fluctuations, okay? And interestingly, if we are sufficiently far in the condensed phase, that doesn't depend on n0, okay? It's really the variance stays the same over a wide range of parameters to leading order. And then we can ask the following question. So we take that random variable n0, we subtract the mean, we divide by the square root of the variance, and you would expect that that has a limit as n goes to infinity. Okay, and we can compute that limit. So for example, if you are in the condensed phase, this converges to a standard normal distribution. Okay, but we can also identify other limiting distributions, and they are all related to the small g that we had on the previous slide. Okay, so what we find is a mixture of Gaussian and exponential. We find an exponential, and we find a geometric distribution depending on temperature. Okay. So, for example, in the non-condensed phase, which is a funny thing to do, you don't have that many particles in the zero momentum mode, but we can still prove that its distribution is given by geometric distribution. Okay. All right. So this is just to show you that we can. If you have the Gibbs state, if you have a trace norm approximation of the Gibbs state, you can get extremely precise results. Okay? All right. Now, what else? I want to say a few words about the proof, okay? And I don't tell you about the strategy of the proof. But one thing should be clear. I told you that we need to, I mean, we have the exponential of h, exponential of minus beta h, and we want to argue that certain terms in h actually don't play a role. Okay, and to do that, you need to control correlations, right? You need to control correlations in the system. So you have terms here with 4 A's and A stars. So you see the interaction there, and you need to show that certain interaction terms are actually small. And how do you do that? Well, you do that with correlation inequalities. Okay, and we have two new correlation inequalities in our work. And I show you one of them because this is more beautiful. Okay, the other one is a little more messy, but this here is very, very beautiful. So let us forget about what we talked so far, and let's look at that thing here. So I assume that I have a Hamiltonian given by two terms. Okay, we have A and B, and I always think of B as a perturbation of A. Okay, this is what this here tells me. B is in some sense small with respect to A. They can both be unbounded. That doesn't matter, but B is A bounded, if you know what that means. If you don't, it's not important. Okay? Now, you should think of H as the Hamiltonian here. It has a one-body part, and it has a two-body part. B, you should think of as here changing that one-body part. It's a perturbation of the one-body part. So you should be able to understand your system with a perturbation of the one-body part, which is usually something doable. Okay? Now, if you understand that, then you can do the following. Say you understand how large the expectation of a certain, of B is, but now in your perturbed Gibbs state, okay? You know how large the expectation of B is in the perturbed Gibbs state, and we take a supremum over minus 1, 1 here. That could be any interval. I don't care about that. It's just to be concrete. Now, and let's say this is smaller or equal to eta with some positive constant eta. Then we have the following bound. So you know that the trace of B squared, and I'm interested in B squared because if B is a one-body operator, then B squared is a two-body operator. And expectations of that are really hard to control because you cannot perturb that guy. This is usually very hard. Okay, so how can we bound this? We have an eta here. We get eta x eta. Okay, so this is bounded by a constant, that too. And then we get a second commutator of the Hamiltonian with B. Well, you could say that looks a little nasty, right? But actually it doesn't. Why? Well, first of all, if A is the Hamiltonian and B is a one-body guy and you commute the two, you know, if you commute something with 4 guys with something with 2 guys, you end up with something with 4 guys. So you don't make it worse. You take a second commutator, you again have something with 4 guys. But, you know, on your way to that point, you learn to control interactions to some extent. Okay, so if this has 4 guys, it's not worse than the Hamiltonian, and you know you learn to deal with that before. So that's the spirit. This term is usually good. This is usually okay for us. And so it's a correlation inequality because we have a first order information and we get a second order information. Okay, this is how this works. And so there has been a correlation inequality of a similar type before. So in that work here, but this is much, much simpler and better. So the point is, in the one that had been there before, this term had been replaced by a 4th commutator and operator norms and additional terms. Okay, so this is the right way to do it. And Well, that it's the right way to do, you can see from the proof. I mean, I won't have time for that, but the proof is so simple, okay? So this here's the proof, basically, up to technicalities. So let me quickly say a few words about that, because it's really beautiful.
Some kind of entropy proof, right? Some kind of entropy inspired proof, right?
Yes. And here's one key ingredient that we realized is helpful, and that is an infinite dimensional version of Stahl's theorem. So first of all, what is Stahl's theorem? Well, let's look at that function here. Okay, we have again some technicalities. Let's forget about that. We have the partition function. It's a function of t. Now, in the case where a and b commute, or in the case of classical random variables, this here is actually the Laplace transform of a positive measure. Okay, it's basically saying that if you take derivatives here, the function you get changes signs from plus to minus, but it always has signs. So you always have convexity at any order, and that's great. Now, it turns out, so for matrices, Stahl's theorem states that, oh, this is also true for matrices. Okay, so also in the non-commutative case, this statement is actually true. And this is not, we have not proved that, okay? This is a theorem of Stahl from 2013 in this reference here, and this has been open for a long time. So this was formerly known as the BMV conjecture, and it was stated in this paper here. Now, what we realized is that if we prove an infinite dimensional version of that theorem, we can use it. And we can use it in the following way, and I even have 1 minute to explain this, okay? So it's really, really simple. So let's look at the partition function. From our assumption here, we know that the derivative of the partition function can be bounded in terms of this here is the partition function divided, the derivative of the partition function divided by the partition function. So that means you can bound a function by a constant you can bound the derivative by a constant times the function. This allows you to control the growth, okay? Now, here's the key observation. The second derivative of the partition function is that guy here. It's called the Duhamel two-point function. Now, the Duhamel two-point function is almost like the second moment, almost. But there's actually the Falk-Bruch inequality relating the Duhamel two-point function to the second moment. Okay, so understanding the Duhamel two-point function is enough. By the way, this commutator term comes from the Falk-Bruch inequality. Now, the main observation is the following. This guy here, the second derivative, is convex in T. And it's convex in T because the partition function is the Laplace transform of a positive measure. Okay, so that's the key input. And then, well, if this guy is convex, you can Z2 prime at 0, you can just use the convexity to bound it from above by an integral. Okay, this is always stays below that. And well, now you use the fundamental theorem of calculus. You get this bound. You are back to the first derivative, which you control. Okay, and this, well, I mean, you use this here, and you bring the Z0 to the other side, and you have it. Okay, and this gives you this bound. So it's super simple. And why is it so much simpler than the previous inequality in the other paper? Because they try to use an approximate convexity for the second moment in T, while you have it exactly for the Duhamel two-point function. Okay, so my time is up. Let me quickly end by saying this is the first correlation inequality. We also have another one to control higher moments. And let me see. Yeah. Okay, so summary, we get an approximation of the Gibbs state and trace norm. We get the two-body density matrix and the exact condensate distributions. we have new abstract correlation inequalities, and one of them is proved with an infinite dimensional version of Stahl's theorem. All right, so thank you very much.